y squared equals x cubed plus b to the fifth. What is this one? So Ira also tells us what this one is. It's a thing he calls the type 2 star degeneration. And what do the spheres look like in this case? So in other words, you get what looks like the affine D8. This turns out to be, again, a degeneration of an elliptic curve. How do I know it's an elliptic curve? Well, there's the equation. What you do is you just resolve the singularity and you find this collection of spheres. Okay. And you can do this game more generally. So he classifies them, morally speaking, it's just a bunch of ADEs. That's the key point. Let's see. Okay, let me do one more thing in 8 dimensions, then I'm going to move on to 6 dimensions. So one more thing you can do is, in addition to having one E8 like this, we can now consider, say, one of our things that has degree 8 and degree 12. How would we build such a model? Well, we have our homogeneous coordinates. I call them U and V over there. Here's an example of an elliptic model, which is compact and does everything you might want. Okay, so what's going on in this model? So here's my CP1. I'm drawing it like a sausage. There's a point here. I'll call it U equals 0. There's another point here. I'll call it V equals 0. At U equals 0, the leading order term, which controls the singularity, is this guy. That's the lowest degree thing, which is singular. Okay, so what do I interpret that as? D8. I go over here. V, flip the roles of U and V. What's this thing? It's another E. What is this? This is the F-theory dual of the heterotic string compactified on the T2. There's an E8 times E8, which is manifest in this picture. So this is literally dual to heterotic on T2. And if you want to consider switching on Wilson lines on the T2, and they break the E8, that just corresponds to switching on lower order deformation of this thing. So by switching on lower order deformations, you break the E8 to something lower. And you'll start moving through different degenerations. You can go from, say, E8 to E7 to E6, and so on. It's all going to follow the same pattern. So this is kind of the first example of a heterotic F-theory type of duality. Okay. So that's all I wanted to say about 8-dimensional vacua, because the goal is eventually to get to 6.
This is K3?
Yeah, that's a K3.
But then I thought you wanted to have a F8 UV also, which is 0.
Yeah. Well, I can make it 0. That's my choice. If I made one thing I could have done, like I said, let's switch on some F, and then I could have produced like an E7 type singularity. So I tuned all of the moduli of the problem. You can still do the other things you want to do, and they'll all be covered by that.
As you go around these singularities in this classification, I would imagine there would be some SL2Z element associated to it. Right?
Yes, that's correct.
So is there a nice way to do?
Yes, there is. So a kind of a 2D way to think about it is you take a bound state of PQ7 brains of different PQ types, and then the monodromy as you go around is dictated by the net PQ type of that composition of a bunch of SL2Z guys. I'm probably going to mess it up,
but I would imagine this thing is telling us what type of PQ7 brains can
absolutely
collide.
Yeah, that's exactly right.
Then the question becomes that in this one.
Yes. Yeah. That's exactly right. Okay.
Are we not allowed to introduce more than 24 subbrains?
So locally, you can do whatever you want. So it's just a question of you try and couple the thing back to gravity. So if we demand a compact CP1, then you're stuck with 8 and 12. If, however, you say, I don't care about P1, I'm just going to keep it as a C, you can put as many D7 brains in this local neighborhood as you like. But you'll have a problem. You'll have to start taking a scaling limit for the metric so that you kind of avoid this bad singular regions. So that's what will happen more globally. So at a non-compact level, you can do lots of things. It's just when you try and couple the thing to gravity that the restrictions start to appear. Okay, so let's go on to 6 dimensions. So what shall we keep on the board? All right. So now we enter the world of 6 dimensions, where we're going to start using the geometric tools we built up to start constructing F3. Yes, it can, but then the fibration is dictated to be trivial.
I mean, it could go wrong with it if it's acyclocity.
Yeah, so you can do things like that. Okay, so strictly speaking, I'm going to exclude that possibility if you don't want to have. Do you want it to be a honest Calabi-Yau threefold? Sorry, twofold, or well, then you're stuck with an elliptic fibration. So I tell you, I want an elliptically fibered manifold over a base. Then you're going to be stuck.
No, but the T2 fiber over T2 can,
Yeah. Well, one way to describe it is you take like a T4 and you perform a discrete quotient. That turns out to just be a degeneration of a particular elliptic K3 where you tune the moduli. So that is a thing you can do, which was studied heavily. So it's not like a ridiculous. It's a totally legitimate way to study it. But it turns out to just be a special case of this kind of thing. Okay, so let's go to 6D. So again, we're going to have our base. But now the dimension of the base is going to be 2. Because we're going to be interested in F theory factorified on Calabi-Yau threefold. Okay, so if we look at the discriminant locus, it goes from being a bunch of points to being a bunch of curves. It's one complex dimension lower. So you could have things like this and so on. And the elliptic curve could be singular here, it could be singular there, and it could be even more singular. We get close to this degeneration, this collision of the two components of the discriminant locus. Okay, so what I'm going to be telling you about is not the most global picture of what's happening, but a very nice local picture of things that could happen in one of these bases. So let's say that you have our base. So special case. Let's take B to be non-compact. And let's imagine that we have a single curve, a CP1, and this CP1 has the property that it has self-intersection minus n. What this means is that if you can write B compact has a normal bundle over the P1, and the first germ class of that normal bundle is minus n. Where by this I mean that I integrate it over the sphere to produce a non-constant sphere. Okay. Now we're going to take n to be positive. So in other words, the self-intersection is negative. So what happens in this case? Well, a very nice result that Morrison and Taylor found is that if this happens, then sometimes F and G are forced to vanish. So in other words, it's always going to have a singularity in the elliptic fibration. So where does that come from? That might get a little complicated. Maybe I'll skip the algebra. The point is that okay, so ask me about this afterwards if you want to know the details. Otherwise, I will skip it. If n is greater than 2, then there are 7 rings on P1. And in fact, you can calculate the order of vanishing for F and G. This on the airplane, so I hope I get it right. Probably not. But you can look up the exact formula in Morrison. This just means rounded up. This one. You can work this out by basically doing kind of intersection theory calculation in the flow thing. I'm going to skip that because it doesn't really figure in too much into the physics that we're going to be talking about. It's just we need to know this qualitative fact that when we have this self-intersection of minus n, the order of vanishing is not arbitrary. There's a minimal order of vanishing for F and G. So what does this mean? So if you have n equals 2, you can see that the order of vanishing for F and G starts, it goes above 2. You can see something interesting happens. The order of vanishing is not 0. So, and if it's 2, it's trivial. Why is that? Well, if it's 2, then we have a special circumstance, sometimes referred to as 1 minus 2 or P1. This thing, the total space for this B, the Chern class for this is trivial. So it turns out to already be a Calabi-Yau space. So in other words, it'd be like a Calabi-Yau twofold, non-compact Calabi-Yau twofold times the T2 factor. So in other words, it can already be Ricci flat without introducing a profile for the axiom fillet. You can also consider the case if n equals 1. And in that case, you can just take you take a kind of a general elliptic fiber over the -1 curve. It's totally fine. These analyses assume that n is greater than 2. When n is equal to 1, you can still talk about questions about orders of vanishing from G. The point is that nothing is forced in any case. Okay, so if n is greater than 2, then there are 7 rings on P1. Now, if we also go through this analysis, we can also see something interesting, which is that there's an upper bound on how big n is allowed to get. What is it? N is less than or equal to 12. So why do I say there's an upper bound? Well, if I plug in n equals 12 into this equation, I get 5. And what's that? That's this guy, E8. If I try to go above that, then I'm trying to produce a 7-brane gauge theory that's beyond E8. But I know that if I try and do an affine extension of anything like this, the Incan diagram classification tells me that I'm going to get something that has some kind of negative norm state. So if I just keep trying to extend, then I'll produce something that doesn't have a unitary gauge theory description. So I can't do that. That's where this. So that's physically what's going on. This is limiting my value of n to be 5 or less. Sorry, 12 or less. Okay. So we might ask, okay, now don't I want to do the same thing? I want to ask, can I put all these 7 rings together and produce a compact model? If I'm interested in coupling the theory to gravity, then the answer to that is yes. If I don't care about gravity, then I don't have to. So the value of Newton, more precisely, is set by 1 over the volume of the things. You can get this by taking the 10-dimensional effective action and just dimensionally reducing on B. So this is the 6th dimension. So if I'm interested in a system that's decoupled from gravity, say like a 6D superconformal field theory, I want this thing to be 0. So I want this thing to be non-compact. Take the volume to be infinite. Okay, so that's like 1 over. So these questions about overclosing the sort of space-time solution, et cetera, that we talked about in the 8th dimension, can again be kind of bypassed if we just talk about non-compact bases to begin with. Okay, so I told you about, it's very important that the order of vanishing for 4 and 6 not be violated in any way, et cetera, et cetera. So now what we're going to see is that if there's a singularity where it does happen, sometimes you can kind of repair it and get around it. So to do that, I first want to tell you about the general rules for constructing something where everything remains in this kind of 4-6 point form. And then we'll see that if we take the singular limits of that, we can sometimes seemingly violate the condition that you were asking about. Namely, can I go beyond the 4-6 singularity? So what are the general rules for building a Calabi-Yau threefold? What we do is we take a certain number of building blocks and we stick them together to produce ever more complicated configurations of CP1s. Then we start asking what kind of elliptic vibrations you can sit over. There's the minimal number of 7 rings dictated by this formula, but there could be even more 7 rings wrapped over. That will depend on the specifics of the Calabi-Yau model we want to construct. So, building a base. The basic idea is that you have these -1 curves of self-intersection -1. Yeah.
The curve on which the thing is vanishing, can it be not T1 but some other curve?
Yeah. Yeah. So certainly in many cases you can wrap 7 branes on various types of Riemann circles. The statement that Morris and Taylor are telling you about is that there's kind of a bare minimum number of 7 branes that are always wrapped. So in many of those cases that you're talking about, the effective field theory will contain, for example, adjoint valued hypermultiplets. You give vacuum expectation values to those things, which in the geometry course does smoothing out the elliptic fiber over that. So in other words, it's always possible to get rid of those singularities. In the cases here, there is no such degree of freedom. And so you're kind of just stuck with this gauge theory over the CP1. So this is what's sometimes referred to, I should have said this, as a non-exable cluster. Or NHC. And so what Morrison and Taylor gave is basically an algorithm for building up general bases using those kinds of non-exable clusters. And so one of the things that they found is that you want to glue two things together, then you glue it via some -1 curve. So you have NHC here, and NHC prime here. And the main idea is that if you look at the effective theory defined on this -1, it's coupled to an E8 flavor symmetry. And what you do is you gauge a subalgebra. We'll call it G left, G right inside of E8, which is where these two things attach together. And that's the thing that actually produces more and more elaborate aesthetic models. So basically what Morrison and Taylor give you is a set of building blocks that you start gluing together through this kind of gauging procedure to start building up very, very complicated looking configurations of CP1s. So let me give you the list of NHCs.
But now when you say gauge and so on, now we are in gauge theory?
Well, there's gauge theory from the 7th grade. So, so this is the 6-dimensional effective theory. The -1 curve theory at low energies just gives you a 6D theory. And it turns out that if you take this line where it collapses to size, it has an E8 flavor symmetry. This is not obvious from anything I've said. It just follows from if we try and write down a Calabi-Yau geometry here. So more precisely what happens is you have the -1 curve like this, and you have a bunch of other components of the discriminant locus that all touch it. Then what happens is in the limit where this -1 collapses to 0 size, all these things align together and produce a 2-star fiber or an E8 flavor symmetry. So that's what happens in that limit, and that's why I'm saying, oh, there's an E8 flavor symmetry lurking in the background. So then we can say, take those 7 rings and then split them up in various ways and wrap those guys on compact curves. So if we take this and wrap it on a compact curve, we can get various examples like E6 and SU3. That's a subalgebra. Things like that. Don't worry, I'm going to go through this in more detail next time as well. But just to close the end, here's the. Does that answer your question? Here's the list of non-fixable clusters. So there's a finite number of these things. You can have a curve of self-intersection -n for. You can have -2. And over each of these things, there's a prescribed gauge symmetry. So for example, the maximal guy, the guy we met over there, would plug in n equals 12. It's associated with an E8 gauge symmetry over this. If you do the same exercise, you'll find that -8 corresponds to E7. And for example, in this case, you get the gauge symmetry G2, G2, and SO7. And another fun one is 5, which is the F4 gauge symmetry. So anyway, so these are examples of things that were just worked out by these guys. It's not obvious from anything I've said, and it takes a whole paper to prove it. But the point is that these things are classified. And there's now an algorithm for building up all possible bases. You just have to take all possible combinations of these things and start sweeping out all possible combinatorial ways of producing general things. And that will produce for you all possible ways of making a base for a Calabi-Yau 3-form. Then, once you have that base, you then ask, how many different ways can I wrap 7 branes over it? In some cases, there's already going to be 7 branes present. That's this statement here. But you can always try to add more 7 branes, consistent with the Calabi-Yau condition. And that would correspond to making the elliptic fibers even more singular. So I should say that in addition to these guys, there's also the ADE Lincoln diagrams made with the -2s. So examples of that type are like a bunch of A-type ones. This would be like A3, and so on. Okay.
Sorry, can you explain what is G and GR? You gauge.
So this is the minimal gauge symmetry that you get. So what you do is you look at the self-intersection, you calculate the order of F and G, the order of vanishing. You then calculate the corresponding gauge symmetry from Kodaira. Then we call that G min. That's the minimal number of 7 rings that must be wrapped into that curve. So in other words, an example of this is we have, say, a -3 curve by itself. It's an SU3. So I'm just telling you the answers. I mean, so if you do the order of vanishings for -6 and -3, you find SU3 and D6. D6 times SU3 is an example of this G left and G right. So I guess here it's G up and G down. But that's the main idea. And then this thing is a subalgebra. D6 times SU3 is a subalgebra of E8. So that's why we're allowed to gauge that subalgebra. So you can do that in various ways and produce kind of complicated bases. Okay.
So when you say wrap additional digital rings, you mean now you are only allowed to wrap them on -1?
No. You can also wrap them sometimes on the other NHC. So for example, in this case here with the -2 curves, the generic thing is just it's just a T2 times this thing. The reason for that is that the total space for this thing is in the base is already a Calabi-Yau. It's already a Ricci flat spacetime. So I can just take a T2 with trivial elliptic vibration, and I'd actually have more than just the minimal supersymmetry. But there's something more I can do. I can wrap additional 7 rings over it. As you do this, you actually introduce additional components in the screen.
No, but I thought on the NHCs it's fixed.
The minimal amount is fixed. Then of course I can start asking, can I make it more singular? So the minimal thing would be like a -2, nothing has to be added. But I can consider D7 rings wrapped on. And the point is that in these kinds of systems, there's additional matter localized at kind of intersections between the 7 rings. And that allows you to kind of Higgs or deform the geometry back down to a system that doesn't have any of these 7 rings on it. So what Morrison and Taylor were really classifying is the cases where there's no more Higgsing available to you. There's no way for you to get rid of the gauge symmetries.
Sorry, but why do they have to be a subgroup of E8?
Oh, because the -1 theory has the E8 flavor symmetry. So the point is that if you take a limit where you decouple the thing, you better have some kind of subgroup of E8 showing up. So the point is that the -1 curve theory is the thing that has the E8. Let me actually close with another perspective on this system here. This will be our only example of an SCFT for the day. So if you take this thing and you consider a D3 ring on the -1 curve, what will you get in 6 dimensions? You'll get an effective string. So to see that, let's write down our space-time directions. So this is our B. This is our R5,1. And let's say that our -1 curve is on the 6, 7 dimensions. Okay. So if we fill this and this, and we have it over here and here, this is some effective string in our low energy theory. What's the tension of that effective string? It's the volume of that P1. So the limit where this thing collapses to 0 size, we get something that has a tensionless string. And as I kind of alluded to at the beginning, this like massless limit or this tensionless limit is where we can expect to get something that looks like an SCFT. So collapsing things down to produce this. So what's another perspective on this thing here? We can use our F-theory heterotic duality to actually track over that this thing turns into the following configuration: an E8 number of the kind studied by Orjava and Heckman, and there's an M5 ring next to it. There's a distance here, which I'll call C, and this is C. We do the map over. Turns out to be nothing but the volume of P1. In the limit where the volume goes to 0, the M5 comes on top of the E8 wall. And this is the limit also in which M2 branes stretched between M5 brane and the E8 wall are giving you streams which are effectively tensionless in that limit. Okay, so.
So this is the original configuration where -1 curve can appear.
Yeah.
And all other cases are just obtained by gazing rays.
Well, not all other cases. So I could have just given you like a -12 curve in isolation. But whenever you want to take more than one non-pinchable cluster and glue them together to make a single interacting thing, then yes, it must be glued via this -1 curve. So basically the name of the game is you take this thing, you glue it like this, and the general base, you start gluing, double prime. Crazy things can happen. Could have something like this. Now, some of these things happen in a general base, and some of these things don't happen in a base that's going to be used to engineer an SCFT. So what happens in a base that makes an SCFT is you get further restrictions on the ways that you can perform this gluing. Basically, it again comes down to calculating the order of vanishings of F and G, and demanding that everything remain in what's called a canirotate form. So, yeah, if you demand that everything is in canirotate form, you'll get some collection of configuration. Okay, so this will probably be the last thing I say. So SCFT conditions. The first thing you do is you look at all of the CP1s that appear in this thing. And what we're looking for is basically configurations of the CP1s, which can simultaneously collapse to zero size. Because we're interested in D3 branes wrapped on these things, and we want to take a limit where things become tensionless. So we're interested in taking limits where we can shrink as many of these guys as possible. That's our SCFT limit. How do we put that into equations? So if I give you a bunch of these curves, let's call them, let's say that the homology class for these guys is sigma i's. And let's consider the following matrix. So this is minus the intersection pairing for that thing. To make an SCFT, what you have to demand is that this Aij is positive definite. This is the condition that in the moduli space of the Calabi-Yau, you can collapse everything to zero size simultaneously. One way to say this, just in field theory terms, say I don't like geometry, I just want to do it in field theory terms, is that if you look at the volumes, these are moduli from the low energy effective action. This intersection pairing also shows up as the kinetic term for the moduli fields. Keeping this positive definite is the condition that you can actually take this limit where everything goes to the origin, meaning that all the volumes have collapsed simultaneously. So if you impose this condition, and you also obviously need to demand that you didn't make an elliptic vibration in the first place, otherwise there's no point in talking about it, then you get some sharp restrictions. So in an SCFT, number one, all configurations are trees. So in other words, you can have things like this. You cannot have, this is the base. You can't have this. What you find if you do this is that the orders of vanishing of F and G, and when you try and combine them with the simultaneous contractibility of the curves, there's no way to combine the two and get a consistent solution. So in other words, you're always stuck with just tree-like structure. That's one thing. So all configurations of trees. Now, there could be lots of crazy trees you draw. Like, I don't know, draw something crazy. That's a crazy thing to do. All configurations are trees. Number two, the number of things that a given -1 can join to is just 2. So, a priori, if I do this gauging rule, you might have said, well,